Stanford University.
Are there other deeper and more profound questions? I'm sorry. What's that?
I don't know if it's deep or profound, but it's a question about last week.
Okay.
So the last thing I remember seeing.
Yes. We're gonna review a little bit.
Okay.
But go ahead.
Well, there was an equation with phi double dot and
Yes.
3h phi dot on the left-hand side, and on the right-hand side was F, force, I guess.
Yeah, minus dv d phi.
So what is acting on what? What sort of force are we thinking about there?
Yeah. All right. Good. You know what a field is. A field is like the electric field, the magnetic field. In this case, a hypothetical, undiscovered field, which is a scalar field. The scalar field exists in space. Yeah. A scalar field in space, and fields have energy. Electric fields have energy, magnetic fields have energy, scalar fields have energy, and the energy depends on the value of the field, obviously. All right. This is an undiscovered field. We don't know how the energy depends on the field, but let's hypothesize. Vertically, let's plot the energy in the field, and I'm going to call it V. V stands for potential energy for reasons that I'll describe in a moment, but just think about it as the energy that would be stored in space per unit volume. The energy density that would be stored in space just by virtue of the fact that the field, which I'm plotting horizontally here, has a certain value. If the value of the field is one value, then the energy is one thing. If the field has a different value, the energy is a different thing, and so forth. And it's very much like the electric energy or magnetic energy that's stored in an electromagnetic field, but different. It's a scalar field. Makes a big difference for some things. All right, so let's plot it. Well, nobody's ever experimentally detected it, so I'm just going to make up a graph. I'm just going to make up a curve. Here it is. Now you might think, well, this is funny. If the field is zero, shouldn't the energy be zero? But the value of the field, which is zero, is somewhat arbitrary. The field has not been discovered. I don't know where its zero is, so I don't know where it should have zero energy. So let's just plot it and make it any old thing. We don't know what it is. This is V of phi. And it represents, as I said, the energy. I'm going to call it potential energy. And the reason I call it potential energy now is because it's the energy that is not associated with time dependence of the field. It's not kinetic energy. It's not energy that's associated with time derivatives. The field defines a certain kind of velocity. It's not a velocity of something in space. It's the velocity of the field itself. In other words, the time derivative of the field. If the field has a certain value, at a later time it has a slightly different value, then it has a phi dot. That's the analog of the derivative of the position of something. Think of the value of the field as a coordinate. It's not a coordinate of a particle, it's a value of the field. If it's changing with time, I'll wait for a minute. Okay, if it's changing with time, there is field energy. An example, just the elastic string. The elastic string is a kind of field in a one-dimensional world, the elastic string. And if the elastic string is vibrating, then by virtue of the fact that each little piece of the string is moving, there's kinetic energy. All right, if we call the height of the string or the position of the string, if we called it phi, there would be a phi dot. And in fact, there would be a kinetic energy of the string, which would be proportional to phi dot squared. Just like, and in fact, we usually define it so that there's a 2 in the denominator. This would be the kinetic energy, or the analog of the kinetic energy of the field. Now, if this were a particle, you would say, I recognize this. It's like 1/2 mv squared. Where is the m? Well, the answer is, even if I put it's not a genuine mass, let's just call it a parameter, a number. A number, what's a good letter for a number? Give me n. All right. How about, better yet, n squared, okay? Why is it better yet? Because I won't have to take its square root, that's why. All right. Put n squared, it's like 1/2 mv squared, where the role of the mass of the mass of a particle is being replaced by n squared. Well, if I then redefine the field, if I change the name of the field, and instead of calling it phi, I redefine a new thing, which I'll call chi. Looks like x, but it's not x, it's chi. It's the Greek symbol chi, and I set it equal to n times phi, then this object over here just becomes chi dot squared. So I can call it the square of the time derivative of some field, having then illustrated that it doesn't matter what you call a coefficient here, you can always eliminate it by a change of definition of the field. Let's not bother, let's just put a 1 here. That's the kinetic energy of the field. We've said there's also potential energy. So the total field energy at any time is this plus v of phi. And now field energy means the energy contained within a small unit box. In other words, the energy density, really. But let's follow a small box in which the field energy is given by this. Okay? The mathematics of it is isomorphic. Everybody know the word isomorphic? Is the same as the mathematics of a particle with a kinetic energy and a potential energy, or very close to it, as we'll see. And if this were a particle, if this were the coordinate of a particle, we would know what equation to write down. Let's go through the steps. The steps are to say this is the energy, kinetic plus potential. Corresponding to it, there is a Lagrangian. This is the energy. Corresponding to it, there is a Lagrangian. The Lagrangian is kinetic minus potential energy, phi dot squared over 2 minus v of phi. And then there's Lagrange's equations. Let me just remind you what Lagrange's equations look like. They look like d by dt of the derivative of the Lagrangian with respect to the velocity. In this case, the velocity is phi dot. Is equal to the derivative of the Lagrangian. Why am I calling it script L? If I'm going to call it script L, let's continue to call it script L over here, or script L over here. Minus the Lagrangian with respect to the coordinate. That's Lagrange's equations. Here's the Lagrangian. We can work it out. The derivative of the Lagrangian with respect to phi dot, that's just phi dot. Differentiating a square just gives you something linear, and the 2 goes away. So dl by d phi dot is phi dot. And if I differentiate it twice, and differentiate it against with respect to time, this becomes phi double dot. second time derivative of phi. In other words, a kind of acceleration. The acceleration of the field itself, simply defined to be the second time derivative, and that's equal to dl by d phi. Because the Lagrangian contains minus the potential energy instead of plus the potential energy, this becomes equal to minus the derivative of v with respect to phi. Now, if this were a particle, and phi was the position of the particle, then dv by d phi would be the derivative of the potential energy with respect to position, and that's the thing we would call force. And it's a function of phi, just as in general the force on an object depends on its position. It might be constant. This object falling in a gravitational field near the surface of the Earth, the force is pretty much constant, but it doesn't have to be constant. All right, so this is basically the equation of motion for a field in a box, and I've assumed that the field is not varying much in space. The reason we can get away with that in cosmology is because space has expanded a lot, or assuming space has expanded a lot, the variations of the field have gotten stretched out. And eventually they get so stretched out that over small regions of space, over this box, the field is very, very smooth and very, very flat. That's an assumption. But this is the field equation for a scalar field with a field potential energy via phi. And it looks like Newton's equations. Now, this is, I was answering a question, but in the process of answering the question, I started the lecture, which is where I was going to start, right? Okay, so let's go back now. This object over here is the energy density, or this over here. If we actually want the energy in the box, we have to multiply it by the volume of the box. So let's keep that in mind and multiply this by the volume of the box. And the volume of the expanding cosmological box is proportional to a cubed, right? The scale factor cubed. It wouldn't matter if the scale factor didn't depend on time. If the scale factor didn't depend on time, it would just be a numerical constant, and the numerical constant in the Lagrangian just cancels out from both sides, so it doesn't matter, but it is time dependent. So the kinetic energy and potential energy both have in front of them a cubed of time. Same with the Lagrangian. When you go from the energy to the Lagrangian, kinetic energy minus potential energy, you have to include that factor of a cubed, the volume. Another way to say it is that this was the Lagrange density, the density of Lagrangian, which you have to then multiply by the volume to find the Lagrangian. Now let's go back and redo the Lagrange equations. Let's do them now correctly, including the a cubed. First of all, there is again, just for comparison, I'll do them over here on the other side of this blackboard. The L by d phi dot is not phi dot anymore, but it's a cubed times phi dot. So we start a cubed of t times phi dot. That's dl by d phi dot. And then we have to differentiate that with respect to time. Let's just differentiate it, d by dt. That's the left-hand side of the equation. The right-hand side of the equation is a cubed times, with a minus sign, dv d phi. Same as here, except there's an a cubed in front of it. Minus. Now you can see immediately, if a were constant, we could pull it outside the derivative here and just factor it out and throw it away, cancel that out from both sides of the equation. But because it's not constant, we have to worry about it. And in particular, when taking the derivative with respect to time, there's going to be a contribution coming from the time dependence of a cubed. That's the new thing. That's what the expansion of the universe does to the equation of motion for a scalar field. The expansion puts a new term in. Let's calculate that new term. Let's calculate both terms. d by dt of this object here has one term, which is just a cubed of t times phi double dot. Now, if that's all there were, again, we would cancel it from both sides of the equation, and we'd be just dealing with an ordinary particle. The second term is the time derivative of a cubed all times phi dot. So let's pull phi dot outside over here and multiply it by the time derivative of a cubed. So the time derivative of a cubed is 3 a squared a dot. 3a squared a dot. Time derivative, yeah, you get that. Okay, that's equal to a cubed minus dv d phi. Now we can divide by a cubed. Okay, if we divide by a cubed, this one goes away. Let's get rid of it. We have to divide here by a cubed. We'll come back to that in a minute. And this one goes away. Okay. So a squared over a cubed, that's called 1 over a. And a dot over a is what? The Hubble thingy. It's not constant, but right. The what? The Hubble thing, right. Right. All right, so what do we get? We get the equation phi double dot plus 3h. Now h, keep in mind, in general it's time dependent. Right? 3h times phi dot equals minus dv d phi, which I called previously or earlier, I called it f. Let's call it f. But keep in mind what it is. It's the derivative of the potential with respect to field itself. So over here, it would be as if there were a force pushing the field down the hill, and so forth. It always pushes down the hill, but it would be pushing forward over here, backward over here, and so forth. Okay, that's the basic equation that you asked me about. Now, do you want to continue the question, or?
Can we figure out a physical interpretation, or is there any way we could or should try to visualize F? If it's a force...
It's just the derivative of the potential.
Okay. We don't have to think of it as a force, one thing acting against another?
It plays the role of a force in the equation of motion here. And since what we're doing is a general form of mechanics of a field now, mathematically it has all of the properties of a force. But it's a force not in space pushing some object, it's a force pushing the field toward lower potential energy. A tendency for the field to move toward, to accelerate toward lower potential energy. Okay, this is our equation of motion. And the interesting thing, of course, is this new term here. And the new term has exactly the properties of a viscosity. This equation now becomes the equation of a field. But think of the field now as the position of a rock, just as an analogy. A position of a rock. Position of a rock which is falling. There's the rock. Its height, we're calling phi, height above the surface of the earth or wherever, and it's falling. and it's falling, let's say, under the influence of a force F, which in this case, let's to be pushing downward, exactly like the force due to gravity. That means the potential energy is increasing upward, and therefore the force is downward. If that's all there was, we would expect the equation to be acceleration is equal to force. The mass, we threw that away. We got rid of it by redefinition. So this object would accelerate. And in a couple of seconds or so, it will be moving hundreds of, 100 meters a second or faster, I don't know. Yeah, well, it'll take some time to get to be 100 meters per second, but not much time, and it would just whiz away. Okay. If it's falling through water, or even better, let's say something even more viscous than water, honey. Moving through honey, it will gradually sink, but it won't continue to accelerate. Now we know what H is for. H is for honey. Right. Okay. It would experience an additional force opposite to the direction of motion and proportional to the velocity. Viscous forces depend on the velocity. The viscous force on a thing at rest, there is no viscous force on a thing at rest. It's only when it's moving that it experiences a viscous force. It experiences the viscous force opposite to the direction of motion. To see that fits with this equation over here, just shift this to the right-hand side, and it becomes minus h phi dot. So the force is along the negative direction relative to the velocity. Looks like a viscous force. So let's fill this space with goo, with viscous goo, and with a viscous coefficient proportional to h, or 3h in this case. Now, in this particular case, if h does depend on time, it would be as though the viscosity depended on time. But we're going to be interested in situations where the viscosity, or where h does not depend very much on time. Does the viscosity of honey depend on time? Sure. If it's in the summer, it's less viscous. In the winter, it's more viscous. So, yeah, you can think of viscosity as depending on time. Makes perfect sense. Okay, now, for the moment, let's suppose that the viscosity did not depend on time. And let's watch what happens. In the beginning, I mean if we drop it from rest. If we drop the stone from rest in the beginning, there is no viscous force because it's at rest. And so initially, it's just phi double dot equals f of phi. It accelerates. All right? The velocity starts to increase according to Newton's law, but as the velocity increases, the velocity increases. So this term becomes more important. Eventually, we'll get to a point where this term matches this term. And when that happens, it stops accelerating. We can write this in the other form. Phi double dot is equal to the external force minus the viscous drag. And when the viscous drag gets up to be big enough so that it matches F, the acceleration stops. That doesn't mean that the velocity stops. It doesn't mean the object comes to rest. It means it just falls at terminal velocity through the terminal velocity is the final velocity that it reaches, the point where the force and the viscous force balance. All right, so you calculate the velocity, the terminal velocity, and it's going to be, let's write it, phi dot. I won't put another symbol in. This is the terminal velocity, or the velocity that it achieves at the point where viscosity balances force. That's equal to the force divided by 3h. The bigger the viscosity, the slower the terminal velocity. And so if the viscosity is very strong, the terminal velocity will be very slow, and the stone will just move very slowly through the viscous fluid. And in that case, if it's really moving slowly, it's very likely that phi dot will be very small compared to v of phi. If it's, it's a rock falling through really viscous stuff, stone, then the kinetic energy is generally negligible compared to the potential energy. Keep that in mind. It's going to come back. But those are the equations of a scalar field in a cosmological background, in a cosmological context. Okay, any other questions about this? Yes?
By using the Lagrangian, are you invoking the principle of least action?
Yes. Yes, we are. And for this, we go back to discussions of field theory and the Lagrangian descriptions of field theory, which is some quarter or another that we taught. But if you don't want to think about the Lagrangians, just take it as a fact that the time dependence in the energy here introduces this viscosity. Now you might ask, what happened to energy conservation? Viscosity, an object moving through a viscous fluid, let's suppose for a moment that there was no force. Okay? It's just, you give it a push through honey, and what happens to it? It slows down and comes to rest. What happened to energy conservation? Well, in the case of real genuine honey, we know what happens. It heats the honey a little bit. Okay? But there was no honey here. There was just the equations of motion of a scalar field. There were no molecules to get heated up or anything. And so we should ask, well, isn't this going to suck energy out of the system? Yes, it is. But why? Okay, so then why isn't energy conserved for this mathematical system with a Lagrangian that looks like this? It's because energy conservation is a consequence of time translation invariance. This Lagrangian, with A being time dependent, is no longer time translation invariant, and there is no energy conservation for an equation for a Lagrangian like this. There just isn't any. So, not surprisingly, that shows up as some sort of term in the equation which mimics a mechanism which allows energy to be lost by the system. Okay, are we all happy? Now, this is one half of the story of the equations for an expanding universe in the presence of a scalar field. The expansion affects the equation of motion through the viscous term, but now we can ask how phi affects the expansion. In fact, what does it do to the expansion? So for that purpose, let's go back to the cosmological equations, not the field equations for phi, but the equations for A. That's the Friedmann equation. I'm going to simplify it and just take the flat space case. You can put back the curvature if you like. It will make no difference to what we're doing because it is small by comparison with the things we're going to keep. All right. So let's write down the Friedmann equation. The Friedmann equation is A dot over A squared, which we can call h squared. This is really an equation for h, if you like, but it's A dot, well, it's an equation for several things. A dot over A squared, and that is equal to 8 pi g over 3, 8 pi g over 3 times the energy density, times what we've called rho in the past. But we now have an expression for rho. Here it is. The thing in the square bracket, not with the a cubed was the volume. The energy density is phi dot squared over 2 plus v of phi. So let's put that in here. 8 pi g over 3, and then two terms, phi dot squared over 2 plus v of phi. Okay. Now let's assume. Why assume? Can we prove it? No, we can't prove it, but let's assume something which we're going to come back to. I'm telling you the equations now. We're going to come back to the motivation for them in a little while. I probably would have started with the motivation if Art hadn't asked me the question. He got me going, so I went into this, but we'll come back to the motivation. Let's assume that the potential energy is that V is fairly large in some units, and whatever units we'll need to say that it's fairly, well, it's large in units that you'll see in a minute. V is fairly large, but it's a very shallow potential, that the potential energy is gradually drawing it so that it decreases off in this direction. If it was tilted the other way, we would simply change the definition of phi so that change the sign of phi and then redraw it so that it was tilted to the right. Tilted down to the right, okay, and tilted down to the right with a very moderate tilt. Yes?
Did we actually say what phi is other than that it's a field, scalar field?
You want a name for it?
Well, you're talking about it has something to do with energy density, and so that's sort of why I'm asking.
You want a name for it? Sure. It's called the inflaton. Has it been discovered yet? Only indirectly. Does it exist? Probably.
So this is a scalar field that somehow has to do with energy density.
It's all scalar fields have to do with energy density. Every field has to do with energy density, period. Every field will contribute to energy density. So every field has energy density, but this one is particularly cooked up to do a certain job. Yeah.
So does all this apply to boson fields?
This is a boson field. Scalar fields are always boson fields.
So, but I mean, every boson.
Every boson could be like this. This one is tailored to do a certain job, and a job that other scalar fields would not do because they just don't have the right properties. The Higgs field being particular, doesn't have the right properties. In particular, its potential is not shallow like this, and the energy density associated with exciting the Higgs field is not very high. We want much more energy density there, but so far this is just a hypothetical description of the universe expanding with a field phi that has a certain property. All right, so if the field phi has a very gradual tilt to it, then phi, think of phi as the stone falling. Now it's falling to the right. Things always fall in the direction of decreasing potential energy. When I drew phi as a vertical axis, I wanted you to think of a thing falling through space vertically, but it always falls toward the direction of decreasing potential energy. And in this case, that means falling down here. Now, if the tilt is gradual, it means that the force is small. We will come back to h. Well, in fact, we have an equation here for h, which we'll come back to in a moment. But whatever h is, it's not zero simply because the right-hand side is not zero. In particular, it has this v of phi here. We'll come back to it. So h is not necessarily small. And in the context that we're going to be thinking of, it's rather large. So h is rather large, big viscosity, big viscous coefficient, very gradual tilt. So thick honey with a weak force pulling you down. What happens? You very quickly get to the terminal velocity. The force is small, h is big, the terminal velocity is small, and this ball, which is really the value of the field, gradually creeps down the hill. And it creeps very slowly, so slowly that the phi dot squared term here, we can check it out, we can use the terminal velocity formula here to tell us what phi dot is approximately, and then check that the parameters, whatever we're choosing for parameters, are such that this term is much smaller than that. But let's suppose we've done that. Then, to a high approximation, as long as it's moving very slowly, h squared, well, again, same equation, h squared, which equals a dot over a squared, is mostly just equal to 8 pi g over 3 times v of phi. And moreover, v of phi is not varying very quickly. Phi is varying very slowly, and v of phi, the height of the potential, is varying with time very slowly. In other words, to a pretty good approximation, the field is standing still, and the value of the potential energy here is just whatever it is on this ramp, a number, approximately just a fixed number. So let's keep that in mind. All right, so this is, how does the universe expand under these circumstances? Well, let's assume that because v of phi is so slowly varying, that as a first shot at it, we can just say that h is constant. Constant over a range of time until this thing slides to an appreciably different height. So as long as this rock up here is maintaining its height or its potential energy, we can just say v is a constant, and let's see what we get. And in that case, of course, h is a constant. What's the solution of the equations of cosmology with a constant h? Remember? Exponential increase, exponential expansion. All right. Why? A dot over A equals h, or A dot, the A dt, equals h times A. The solution of that equation is an exponential expansion. Time derivative proportional to the same object with a constant coefficient, or approximately constant coefficient. A expands like some constant times e to the ht. And we have h. What is h? Let's solve this equation for h. Let's get rid of a dot over a here. And we know what h is. H is equal to the square root of 8 pi g over 3 times the potential energy on this ramp, all under the square root. So if we know the height of the ramp, of course we might want to fit this to experiment if we if we were at the time at which this was taking place, if we could monitor how fast the universe was expanding, we would simply fit v to observation. But the things we're interested in here are taking place in the very early universe. Let's first be clear. This is a theory of the very early universe. It's a theory of the inflationary early starting point of the universe. At that time, v was believed to be rather large in any kind of sensible units, which means that the universe if this is a correct theory, the universe was exponentially expanding. Where is it? Exponentially expanding with a large coefficient. How large? Well, roughly the guess that it would be natural in cosmology would be that the doubling size of the universe was 10 to the minus 32 seconds. So it's really going. It's really accelerating, really expanding at that time. This is not the theory of the current accelerating universe. This is a theory of the early universe. We'll describe what happened later in a little while, but this is the exponential expansion during inflation. Yeah.
Probably not drawing the right connections, but large viscosity and low gradient and rapidly exponentially expanding universe just seem to be opposites. I know
It's
that
phi that's moving slowly, not A. It's phi that's moving slowly. Because it's moving slowly, the potential energy stays more or less constant, and it's the potential energy which is driving the expansion of the universe. It's the derivative of the potential which is driving phi to move. But it's the potential energy itself which is driving A to accelerate. So they're quite different things. Right. Right. It's not A which is experiencing viscosity, it's phi. So there's no viscous drag on the expansion of the universe. That's not what's going on here. The viscous drag is on the evolution of the field, which is keeping it pretty constant. All right. Why should we be interested in a theory in which the universe was expanding very rapidly for possibly some significant length of time, time now being measured in units of 10 to the minus 32 seconds? Why should we be interested in such a theory? The original guess about this, which went back to Alan Guth in 1980, did not seem terribly compelling, and yet cosmologists caught onto it very quickly, cosmologists and theoretical physicists. By now it has been confirmed, but it's one of the stories of theoretical physics and guessing, and the guess was a kind of a way out guess. The puzzle, there were two puzzles that this was addressing. They were similar puzzles, and in fact they are related to each other, but the first puzzle had to do with particles called magnetic monopoles. Now, none of this inflation has ever been discovered yet. Oh yes, I take that back. This inflation is now, by now, well confirmed. Inflation being this experiment, or this exponential expansion. We know that that really did happen, or at least we know with some degree of confidence that it really happened. And it happened long enough that this exponential expansion caused the universe to expand by at least e to the 60. A lot of expansion, at least e to the 60. We know that, and we're going to come to how we know it, but not yet. Okay, so so why should one be interested in stretching the universe so much? Well, the first reason was monopoles. What are monopoles? Monopoles are once again a set of particles that have not been discovered. Why should you introduce one crazy theory with a totally undiscovered field to worry about particles which are also undiscovered? And what was it? What was trying to be explained? Not the fact that you didn't see those, well, yes, the fact that you didn't see those particles in a certain sense, but not the fact that those particles were undiscovered. Yes, I take it back. You were trying to explain the fact that those particles were undiscovered, but not that they were undiscovered by particle physics experiments, namely that they just weren't out there in the universe. And the way the argument goes, a magnetic monopole, let me tell you first of all what a magnetic monopole is and what the expectation for their properties is. A magnetic monopole plays the same role with respect to magnetic field as an electric charge plays with respect to electric field. It's simply a source, a point source or an approximately point source of magnetic field with magnetic field radiating out from it in a Coulomb pattern, exactly the analog of an electric charge. Magnetic monopoles according to current theories, have never been discovered in the laboratory because they're very heavy. How heavy? Somewhere's up near the Planck mass. That's to put it all in a nutshell. Magnetic monopoles are believed to exist. They exist in most unified theories. I would say they exist in every unified theory that we can think of. And in most theories, they are very heavy. Heavy by comparison with ordinary particles. The fact that they are very heavy, perhaps 19 orders of magnitude heavier than the proton, would easily account for the fact that they have never been seen in the laboratory. Okay, but now let's go back to the very early universe. Remember, in the early universe was hot. And when it was hot enough, there was enough kinetic energy in the form of photons and other particles that you didn't need an accelerator to make elementary particles. At one point, the temperature was high enough that photons would scatter off each other and produce electron-positron pairs. Even earlier, it was hot enough that photons would scatter off each other and produce protons and antiprotons. Well, if you go way, way back to what physicists thought of as the very, very beginning, the temperature, according to theory, was hot enough that it could have created magnetic monopoles, pairs of them. Just like you create pairs of electrons, electrons and positrons, when the temperature was 26 orders of magnitude higher than something or other than the temperature for electron-positron pairs, it should have made monopoles. Right. Now, you can say to yourself, well, why? I mean, okay, this is wild, wild speculation. Okay. Nevertheless, every theory that we knew about seemed to contain these monopoles. Where were they? First of all, monopoles can't easily disappear. They have a charge. They can't just disappear. What can they disappear into? They can't become electrons and photons and other things, because electrons and photons and other things don't have a magnetic charge. Magnetic charge would be conserved, just like electric charge. So these particles, unless they annihilated, and one can estimate how likely it is that they all annihilated, not likely. So in the course of the universe, as it evolved, we would have expected to find some population of magnetic monopoles floating around in space. Maybe not a very large density of them. The universe expanded a lot. Since the time of decoupling, it expanded by a factor of 1,000. Since the time that it was hot enough to create monopoles, according to the standard theory, it would have expanded a lot more than that. So they would be pretty dilute. Right? But they don't seem to be there. Now, why do I say they don't seem to be there? They would have an interesting effect on the magnetic fields of galaxies. If there were charged particles around, what happens if there's an electric field around and you have a population of electrically charged particles and antiparticles? They discharge the field. A bunch of particles, if you had a capacitor creating an electric field across here, and in here there was electrons and positrons, let's say, plus charges and minus charges, plus charges and minus charges. This is the plus side of the capacitor, this is the minus side of the capacitor. What happens? The plus side of the capacitor pulls over the negative charge, the minus side of the capacitor pulls over the positive charge, and it discharges the field. It discharges the field. In the same way, if the population of monopoles was as large as theorists had estimated, and if they lived forever, and they sat there in the magnetic fields of galaxies, over the period of the age of the universe, they would have discharged the magnetic fields of galaxies. The magnetic fields of galaxies have not been discharged. They're there. They exist. So it became pretty clear that there's no significant population of monopoles out there, even though the standard theories of the times in 1980 and so forth standard cosmological theories predicted that the universe was hot enough to create them, and then in the process of expansion did not completely dilute them away. Right. That was one argument, that was one set of facts. The other set of facts was the homogeneity of the universe. Not today's homogeneity, but the homogeneity at the time of decoupling. How do we know it was so homogeneous then? By looking at the cosmic microwave background in different directions of space. As time went on, the temperature of the microwave background became better and better measured, and it was measured in different directions. The flux of radiation coming in, as well as the temperature of it and its distribution, were measured to very, very high precision all over the sky, and one found that it was absolutely, or almost absolutely, at the time in 1980, it was absolutely uniform to 1 part in 10 to the minus 4 or something like that, 1 part in 10,000 or even better. It was absolutely uniform on the sky. And so that raised another question. It raised the question, why is everything so, why at that time was everything so darn smooth? No standard theory of cosmology could explain, if you start with a small universe, very, very hot, it's likely to have all kinds of fluctuations and bumps and lumps on it and so forth. And expansion from a standard expansion would not have flattened it out and smoothed it to the degree that it was known to be smooth and homogeneous. The guess that Alan Guth made was that very, very early, after the monopoles had been produced, and after perhaps the universe had a highly complicated texture, an enormous amount of expansion came. It diluted the monopoles so that enough expansion will dilute anything, so that the presence of monopoles was just diluted to the point where there were many, many fewer of them than had been estimated. And it also diluted the textural lumps and bumps that one might have expected to be there. Now, nobody could prove that they were there. You could just say, well, the universe just started very, very smooth, and it stayed smooth. You could have also said the universe started with no monopoles, but there was no good reason for it. With one shot, the idea of a very, very early, extremely large amount of expansion can solve both problems. Flatten everything out or smooth it out, just like a blowing up balloon. Balloon gets smooth, and dilute the density of these monopoles. It was estimated, the estimates vary to some degree, but it was estimated that if you wanted to make the universe as smooth and flat as it is, from a known starting point or an unknown starting point, but except that the unknown starting point is not terribly smooth, if you want to start with something which is not too smooth and blow it up to its present smoothness, you had to have what is called approximately 60 E-foldings. 60 E-foldings. An E-folding is a multiplication by E. E is 2.7. Right? In order to arrange the facts to be consistent with the known flatness and smoothness, you needed approximately 60 E-foldings, or a factor of E to the 60, which means that this HT factor here had to be at least 60. That in itself tells us that this ramp must have been rather shallow. The universe had to stay on the ramp for a sufficiently long time for it to have grown by factor E to the 60. It doesn't tell you any details. There's all sorts of ways that you can change one thing and change the other thing. But the working number is that there had to be e to the 60 or 60 e foldings of inflation in order to simultaneously account for the lack of monopoles and for the lack of structure in the universe at the very earliest. Yeah.
Is there a theory about why it wouldn't be completely chaotic before inflation started?
There is no reason why it could not be completely chaotic. That, no, no. 60 would be enough to start with something which was very chaotic and rough and stretched it out.
I mean, mathematicians talk about extremely
Yep, but
non-differentiable. You can't.
okay, so maybe it was 70. 60 is the minimum. 60 is the minimum you make your assumptions worse, you need more.
But with magnetic monopole, you can kind of predict how many there would have been. So that could give you a firm 60, but I don't see how you would have a.
It's only telling you that there were at least 60. Now, if you say that the universe at the very beginning was fairly rough, but not very rough, it's again about 60. If you say it was rougher than that, well, then it becomes 70. If you say it was more texture than that, it becomes 80. Minimum. Minimum number of e-foldings is 60. Now, again, these numbers are not hard and fast. By changing the theory in this way and this way, you can probably bring it down to 40 or 50. But one doesn't, there's room for pushing numbers around a little bit. But I would say, with reasonable confidence, we know that the inflation took place so as to expand the universe, if not e to the 60, e to the 50, or more. An upper bound we don't have. Could it have been e to the e to the 10 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 to the 60? Yes, it could have been. Nothing in observation tells us one way or the other. That would be very remarkable, because to do that you would have to make this extremely shallow, and you'd have to fine-tune the shallowness of it and so forth. But still, there is no known upper bound. There is a lower bound of about 60 e-foldings that's necessary to understand the flatness and so forth. Okay, so that's where things lied around 1980. Alan Guth postulated that this exponential expansion, and in order to drive the exponential expansion, he postulated exactly a potential which looked something like this. The first round of theories was not quite right. It got into the form that I'm describing now after a year or two. Andre Linde and other people sort of straightened it out. But and I don't want to go back through too much of the history, because some of the history was wrong. Not the history was wrong, the physics was wrong. But ultimately, it got straightened out to where the theory looked pretty much like this, with a shallow ramp which supported this inflationary tendency for at least 60 e-foldings. Now, one interesting thing is, if the number of e-foldings were just barely 60, that would mean you are on the edge of being able to see exactly what it is that the inflation was invented to get rid of, right? Inflation was invented to get rid of something. This is how much you needed to flatten it to the current flatness. What if it were right on that edge? If it were right on that edge, it means you should be on the threshold of, in the next round of experiments, being able to see some additional curvature in the universe. So one of the things that will be hunted for by the Planck satellite and other rounds of observational cosmology will be to see if the universe really is flat. Might it have curvature, spatial curvature? Might it have positive curvature? Might it have negative curvature? And the fact is, inflation does not tell us whether there was more e-foldings than 60. It just tells us there had to have been 60 in order to account for the present data. Always in such circumstances, it means that you have a chance in the next round of if you're on the edge, So this, we will come to why this is so important. It is important, yeah.
Yeah, how does this relate to the temperature of the universe, this rapid expansion?
Yeah. By what? All right, so the first impression, which is close to the truth, is that this rapid expansion cooled the universe. Expansion cools things, and if it was just classical physics, and you had some heat in a box and you exponentially expand the box, very quickly it will cool to negligible temperatures. So the first answer to this is, at least in a classical universe, this rapid expansion would have cooled it down. So our first statement, let's say, is that it was cold, very cold, during this inflation, during this period here. Very cold, because the heat got diluted. Everything got diluted. The space was empty. It was expanding rapidly. It was empty of all kinds of structures, empty in the sense that they had been diluted. Ordinary particles were diluted. Monopoles were diluted. Everything else was diluted. Okay. Empty as hell and cold. Okay. Now, this could not go on forever. Why not? No theoretical reason. If this potential had some other shape, it could go on arbitrarily long. But we know it didn't go on arbitrarily long. We're here. The universe is not doubling once every 10 to the minus 32 seconds, so something happened. The natural guess is that this potential did something different. It had a plateau, and it came to the end of the plateau. Why it had a plateau, and why the end of the plateau looks like this is a mystery today. We don't know. What we know is that this is a pretty good representation of cosmological data. And what about today? What about the bottom here? The bottom represents today. The potential energy of the field is very small. We'll come back to why in a little while. All right, so if this is your model, if this is the model that works, how does it work? First question is, how did the universe get here in the first place? Nobody knows. That's part of the initial condition. And of course, initial conditions in this context mean that's how far you can trace back with anything like observational data. So we know from observational data, CMB data and so forth, that there was a period of inflation. We must have started up here at some point. How we got there, we do not know. It's a rather completely arbitrary thing to start us up there, and it requires a theory. It requires a theory of some cosmological setting to say why did we start here? Did we really start here, or did we come down from some other place? We don't know. We don't know. But tracing back as far as we can go, it looks like a good bet that we started somehow like this, and gradually rolled down this hill, taking long enough that 60 e-foldings happened.
Where do we think the onset of inflation occurred in relation to decoupling?
Oh, much before. Much before. Much before. Much before. All right, now, what happens when you get to the end of this plateau? When you get to the end of this plateau, if it's steep enough, viscosity becomes less important. First of all, viscosity becomes less important for two reasons. As you go down the hill here, h gets smaller. Remember what h was? H is proportional to the square root of the energy, of the potential energy. If this potential energy gets smaller, then h gets smaller. On the other hand, F, the force, gets bigger as you go down the hill here. So viscosity becomes less important, force becomes more important, and the expected result is that you would slide down, once you got to the edge here, you would sort of slide down relatively quickly. Inflation would stop. And in the process of sliding down the hill here, energy was released. Potential energy, the potential energy of the field disappeared. It's true in an expanding universe that energy is not strictly conserved. But even in an expanding universe, there's some memory. If it's not expanding too fast, you still do get to use at least approximately energy conservation. If this potential energy suddenly disappeared, it will be made up for by kinetic energy, by something. So it's thought that as you went over the hill here, the potential energy, V, got converted to something else. Well, one thing that it would get converted to is the velocity of the field, obviously. But then eventually you get down near the bottom. When you get down near the bottom, let's assume there is a bottom, and you get stuck at the bottom. Where is the energy? The energy somehow got converted to particles, got converted to heat. At some point, all of this energy up here got converted to heat. That's what is thought. The energy got converted to heat, and that, at that point, that's where we usually start what we call the Big Bang. When this vast amount of potential energy, which is believed to have been there, a very large amount of potential energy, suddenly got released, fairly suddenly, it got converted to heat, and that heat was the starting temperature of the universe when it began as a hot Big Bang. So the Big Bang has to do with what happened as you slid down here. As you slid down there, lots of heat was generated. The heat that was generated replaced the right-hand side of this equation by perhaps radiation domination, and that's the period when standard cosmology started, as you go down this hill here. Yeah.
In the Higgs field, you have a constant field, and excitation of that field are the Higgs boson.
Yes.
So when you get to this valley down here, are you getting inflatons being created?
Yeah. Yeah.
So you're
Yeah.
filling the universe with inflatons, and then
Right.
they're decaying?
Yeah, exactly. Well, when I say exactly, that's one nice theory. That's one nice way that it could have happened. The inflaton field is itself a field that has quanta. Those quanta are called I guess they're called inflatons. Yes, they would be called inflatons. And so as it rolled down here, you could either think of the field as increasing, or you could think of it as the production of lots of inflaton particles. If these inflaton particles themselves were unstable, they could decay into electrons, positrons, photons, and other things. And that would be one explanation of how all this energy got converted to heat and particles. So yes, that is one story, which in some form is probably the right story.
Now, there was the bottom of the trough there at the end.
Yeah.
That's where space actually began.
Well, it's not where space begun. It's where somewhere's down here on the slide down here is where the Big Bang that we normally think of as the Big Bang began. The hot Big Bang.
Down up to that point, to the left there, space did not exist. Where am I?
Why do you say that space didn't exist?
Well, because the Big Bang did not expand into space that existed. It created space, did it not?
A huge amount of space was created by the inflation. That's what the inflation did, is it blew up this fictitious balloon. Well, we could, I'm not sure exactly what creating space means, but let's suppose what it means is it makes space bigger. We don't understand the starting point, but let's take as the starting point some little tiny, three-sphere of space, in want of anything else. Right? What will we mean by saying creating space? We mean we made it bigger. We made it bigger to be able to move around in and have stars and galaxies and so forth, and have interesting spatial relations called triangles and things of that nature. And that simply involved expanding the universe by a factor of, what's e to the 60 would be about 10 to the 25 or something? 10 to the 26. So 26 orders of magnitude of expansion is where the space was created. Then, after the space was created, it was empty. It was empty, but it was full of potential energy. To say it was empty is not quite right. It was full of potential energy. Now, this potential energy was actually in the form, roughly speaking, at that time, of dark energy, except it was of a much, much larger value than today's dark energy. It was potential energy. It was the potential energy of this field. That got eliminated when you rolled down the hill. Something had to replace it. What replaced it, according to theory, was particles, heat, light, and all the stuff that the universe began with. It began with in the sense of standard cosmology. Okay. It rolled down to the bottom. What about the bottom? Was there any potential energy left over at the bottom? Yeah, and what do we call it today? Dark energy. Right. The universe is still believed today to be expanding exponentially, but with a tiny Hubble constant. Not once every 10 to the minus 32 seconds, but once every 10 billion years. That requires a very, very small potential energy here, and it's what we today call the cosmological constant. Yeah.
If they don't find the magnetic monopoles, do you make the 60 bigger, or do you decide?
No. The monopoles were diluted out of existence during the first round of during.
I thought you said we were on the edge of maybe seeing.
Oh no, actually, I don't think we're on the edge of seeing monopoles. We're on the edge of seeing some curvature. I don't think there's any chance of seeing monopoles. We know that the galactic magnetic fields were not unwound, but the precision with which we can say anything about monopoles from the fact that the magnetic field was not unwound is not very good. But what we can do is measure the curvature of space. The curvature of space has been measured to some precision. It's less than 1% in some units. And in the next round, it will go down possibly 2 orders of magnitude, and we may discover that space is curved. The tightest constraint on here is the fact that space looks flat. In other words, there was enough inflation that it flattened things out to a degree where we at present cannot measure any curvature to space.
So if you don't see it, can you make your 60 bigger?
Yeah, we'll make the 60 bigger. Right.
So is the bottom of the hill there, the leftover energy, is that the vacuum state energy?
That's the vacuum state energy of today. Now, why? So in some sense, there's a nice unified picture of inflation and dark energy. On the other hand, it's a complete mystery why the number down here is 120 orders of magnitude smaller than it was up here. That's part of the mystery, why this, I've drawn it on the blackboard as if you could see this. But on the scale of what's drawn here, it should be 120 orders of magnitude smaller. And that, of course, is the mystery of the small cosmological constant. Yeah.
So if I understand what you're saying is during the expansion, there weren't particles, radiation, whatever, it just space expanded. But then how does that explain, you were saying it smoothed things out. What was there to smooth out? If the particles came
The
after.
curvature of space, the geometric curvature.
Okay, but how did it thin out the magnetic monopoles that didn't get created until later on?
No, they were created, you're in trouble if the monopoles are created later on. You have to juggle the time scales here to make sure, or time and energy and scales and so forth. Right, good. The question is, when this fell off here, how hot did it heat the universe? Did it heat it up to the Planck temperature? In which case you were back exactly where you started, plenty of energy to create monopoles. Or did it heat it to something more moderate and modest? That depends on the details. Yes, you're right that there's a question here. This is called reheating, incidentally. Why it's called reheating and not just heating, I don't know. But it was called reheating, and reheating took place and created a certain temperature. It is essential that that temperature is low enough that it be below the threshold for creating monopoles. Otherwise, you're back where you started. If monopoles were created on this leg of the journey over here, you're back in the soup.
Are monopoles considered particles?
Yeah.
Okay, so those were particles.
But very heavy ones.
Okay, but they existed before expansion happened.
They may have existed before expansion happens, or they may have failed to have been produced for the simple reason that it wasn't hot enough. Yeah. Now, you have to juggle numbers to get this to work out, but the numbers aren't crazy. So we're down at the bottom of the trough.
Is there any overshooting expected?
No.
Climb back up the other side?
No. Well, a little bit. But the reason that it doesn't overshoot is because of the friction.
Okay.
The friction was enough to keep it from overshooting.
You know, what caused that curve to suddenly drop?
Yeah, we don't know. Yeah, this is a parametrization that fits observation. We don't know why it was so flat up here, and we don't know why it didn't continue to be flat. There's no theory of it.
But even though there's no particular explanation, is there reason to believe there was a cause for the inflation to stop? We just don't know what it is? Or just
Let's put it this way. I think the only known answer to any of these questions, when I say known answer, I don't mean to say that it's known to be right. I mean, it's the only answer around, is anthropic. That the universe may be extremely big and may have many, many, many different environments of all different kinds. And you can ask, here we are, what did it take? What kind of environment was necessary for us to exist? Now, the thing is, a lot of this is necessary for us to exist. Certainly, we couldn't exist if the universe was as big as a peanut. So it had to have evolved and expanded. I didn't want to get into that tonight, but the rough structure of this curve is dictated not only from observation, but most of it and large parts of it are necessary for the universe to have evolved to something that looks like what we live in. So I'm going to come back to that. But other than that, we have no explanation of why the features of the curve are like this. We don't know.
could it be just not even causal? I mean, in physics, everything that happens, there's a cause. When the universe goes through the radiation phase or whatever, there's a cause. And this would be the first time I came across something where there was no cause why something radically changed. And Is it just they don't know what it is, or there isn't a cause, or is that not even a valid question?
The answer is unknown. The answer is unknown. Some things are unknown.
Yeah.
Some things are unknown. Yeah.
The horizontal axis is phi. The horizontal axis is the field value phi, right?
Mhm.
So phi is getting larger, but then you said it could be getting smaller either way.
Well, where you put the zero of phi is completely arbitrary, where you decide to say phi is equal to 0. You can put it here, you can put it here, you can put it here. You might like to put it here where it is today and say that's the 0 of phi.
Can we say anything about how the changing value of phi relates to time?
It changes with time.
We know anything about the
You
characterization?
mean today?
Throughout that
Where's
Throughout
time
the-
on the graph?
Time isn't on the graph. But we can mark off times. This is 10 to the minus 32 seconds. Well, this is the start. 10 to the minus 32 seconds, 10 to the minus, twice 10 to the minus 32 seconds, blah, 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 blah. Is 60 times 10 to the minus 32 seconds. That's what you need here. That's what you need here. 60 times 10, if it doubled, or let's say it multiplied by e every 10 to the minus 32 seconds, then in those units, by the time it went over the edge, there were at least 60 units of e-foldings, maybe more. So time ticked off here. And then, relatively quickly, you went down the hill here. How long did it take to go down the hill? Probably more than 10 to the minus 32 seconds, probably a lot more, but on the scale of ordinary time, pretty quick. Okay.
Did you say earlier that it's impossible for the energy to go back up on the far right side of that curve? And if it can go back up, what are the implications of it?
If it can't go back up, or can it?
I thought you said it could not. Maybe I misunderstood.
Yes, that's correct. It cannot go back up. Remember that the equations of cosmology have a friction term in them. The expansion of the universe today is big enough to provide a friction that would make it very unlikely for this to spontaneously go up the hill. Right, so you're sitting in or another way of saying it is it was the friction term that brought it to rest. It may have overshot, it may have even rung a couple of times, but the friction term due to the expansion of the universe would have slowed it down, would have come to rest, and then just like any kind of object in a viscous, a rock sitting at the bottom of the sea is not going to suddenly spontaneously come up to the top.
Do we have an idea how the temperature varied during that time?
How the density varies? The temperature. Yeah, the temperature was very cold during this period here. Okay, and then during this period here, when particles were dumped into it, we don't know with any detail what the temperature was that it was heated to by the time it got down to here. But what we do know is it had to have been hot enough to create all the particles that we know and love, quarks and everything else. So it had to be in the the range of huge particle physics temperatures. But
Number of degrees.
okay, so I always have to work this out. Room temperature is a 40th of an electron volt. That's room temperature. We're talking about temperatures which were high enough to create proton-antiproton pairs, or very likely much, much hotter than that. So a 40th of an electron volt for room temperature, that's 300 degrees. A billion electron volts to create proton antiproton pairs, so that's a billion times times 1 over 300 times 1 over 40. So whatever it is. It's 10 to the 11th, 10 to the 12th degrees, something like that. Somewhere in a trillion degrees. or hotter, that's probably on the very, very low end. Remember, you have to have heated the universe up enough to, among other things, you had to heat the universe up enough to create the baryon excess, to create proton-antiproton pairs and that sort of thing, but probably much hotter than that. So,
Bosons associated with that,
yes.
with that actual field?
Yes, those bosons are called, yes, they are, on the way down here, they decay, and in the process of decaying, produce the usual particles. That's the theory. Yes. That was the same question that was asked earlier. There are bosons, those bosons decay, and what do they decay to? Photons, electrons, quarks, anything that creates ordinary energy density. So, and dark matter for that matter. Probably more dark matter than anything else.
Question, please. It looks, what you said is that the field always moves in the direction of its potential energy.
Moves in the direction of decreasing potential energy.
Excuse me. And so what you're illustrating is it looks like the universe has definite potential energy along the time of expansion and inflation, and that would somehow hit a low point in potential energy in the universe. Is it to say that that potential energy is there to stay and there's no other direction for it to go?
Sure looks like it.
So, that's to say then that the expansion of the universe has no bearing effect on this scalar field.
That's right, at the present time. That's right, at the present time, it looks like we're stuck at the minimum here, and unless something else happens that is not built into the equations at the moment, we'll stay there forever. Now, it's interesting to ask, what happens if we stay there forever? If we stay there the universe exponentially expands. Now, it's true, it doesn't exponentially expand very rapidly, but still, every 10 billion years it doubles. It takes how many times? Over 1 trillion years, it will expand so much that basically the galaxies will have all receded from each other, be moving away from each other outside the horizon. Our galaxy will be alone. There will be, well, the Andromeda might, by then the Andromeda probably will have merged with our galaxy. Everything else is moving apart, and we will truly be alone out there. There'll be nothing else but the Milky Way, and the cosmic microwave background will have cooled to a temperature which is way below detectable. Everything else in between galaxies will have stretched out and diluted to a point, not by inflation, but by the current inflation which is taking place, the very slow inflation. In a few trillion years, I think it's a good deal less than that, but I would have to think about it. But in a few trillion years, our galaxy will be absolutely isolated, and physicists who live on it at that time will have no way of knowing that they are part of a population of large numbers of galaxies. They will not be able to measure anything about astronomy. They will not even be able to tell that they're undergoing an accelerated expansion. Remember, how did we discover the current dark energy? We discovered it by astronomy. We discovered it by looking at the CMB. The CMB, cosmic microwave background, it will have cooled to a temperature which makes it undetectable. Everything in astronomy will have departed and gone out through the horizon. And so we won't be able, not we, but they, will not be able to tell that they're in a inflating, accelerating universe. If they come on the scene without history books and so forth, at least for some period of time, let's imagine it, but for some period of time, they'll look around at a universe which is 50 billion light years big. They won't see anything. They won't be able to tell us 50 billion light years. They'll maybe send out probes, and the probes will go out a few thousand light years and come back and tell them, I saw nothing, there was nothing out there. and they will discover themselves a unique phenomena sitting at the center. Well, of course, they'll call themselves the center, and one and only one such thing, and they will be puzzled. They will be puzzled. And then some smart young guy will come along and he'll say, hey, you know, maybe there are lots more out there, but maybe the universe just expanded a lot and they just went away.
Is it clear that all this started from a point source?
What does that mean?
That there weren't other point sources that
Point
could
sources
be
of what?
expanding back through us?
Point sources in what?
In,
Zero space.
Hmm?
Zero space.
In what?
At the point there was no space.
At the point.
Before the creation of space itself. This is.
Yeah, I know. But if there's no space, but only this tiny little nugget, which is what is it a point source in? You're imagining that this thing is in some other space, but that's the wrong idea.
That's right.
couldn't there be more than one phi space?
The bulk. It's
Could have been more than one. You'll have to ask somebody else.
Is the 10 trillion years from now a situation analogous to perhaps what we can't see beyond our expanding universe?
Yes, but yes, it will be analogous, except that everything apart from our own galaxy will be out beyond that point.
So the radio astronomers in that galaxy might be able to detect old transmissions of the Groucho Marx radio show, for example.
I don't think so. I don't think so. They will be redshifted to the point that they will be, yeah, not very funny. Let's put it this way, not too funny. It'll take a long time to get the joke. Wait a minute, there's too many questions. I'm going to start at this end and sweep across. Okay. Well, you had a question. Let somebody else get a question.
Is there
Leonard.
any idea how heavy the inflaton particle is?
Yeah. Well, okay. No, there is no. The mass of the inflaton particle has to do with the curvature of this down at the bottom here, and we know nothing about it. We know nothing about it. The only thing we know is it's not so light that we would have produced it in accelerators. That's about all. Okay, wait, we're going to sweep across. Okay.
Is this phi also a function of spatial coordinates?
Oh, absolutely.
So is this like an average?
Yeah. Again, phi might have started with lots of ripples, but in the process of this inflation taking place, those ripples got stretched out. So after a couple of e-foldings, the ripples would have been, pretty much eliminated locally, and you can forget them. Although we'll come back to that. I mean, that's, yeah, well, let me see. Okay, yep.
When you talk about ripples, were those quantum fluctuations?
No, let's quantum fluctuations we will come back to. For the moment, let's just imagine classical waveform and it gets stretched out. That's the primary main thing that happened. Superimposed on top of that were quantum fluctuations, and they will play an enormously big role when we come back to it.
And what exactly are quantum fluctuations in that context?
Let's wait, because that's going to be a serious issue that we'll come back to. Okay, you're in my next angular.
Oh, okay. Should we today be seeing galaxies slipping over the horizon?
No. The horizon is so redshifted, and all we see out there is cosmic microwave background. When we look back that far, first of all, we're seeing the universe at an early time before galaxies even formed. So when you look way out there, and the furthest we can see is to the surface of decoupling, the surface called the surface of last scattering, but that means the place where the universe was opaque. That's pretty much out near the horizon, okay? But we can't see further than that, and even if we could, we would be looking back so early that there would have been no galaxies. And so the answer is no, we can't see such things.
So it's only at a later time that these objects are going to slip over the...
Well, we'll never see them slip over. When we look out, we will always see pretty much the same thing.
As an information theory war veteran, is it easy for you to say that future astronomers will really have no information about the origins of the universe?
Well, what we'll have is the observation, not we, what they will have if they still exist and stars still exist and so forth, what they will have is their little galaxy. And in an otherwise completely empty space, it's very hard to see how they could do any observations which would directly tell them that they were in a space which was inflating once every 10 billion years or once every 20 billion years. I can't offhand think of anything that they could do short of sending out probes which would take, of order billions of years to go out there and come back and make measurements on the whole global structure of the universe. Short of that, I can't see how they could tell what the expansion properties of the universe were or anything else. They could do that. They could take tens of billions of years and explore, but they can't go too far, because if they go too far, they go outside the horizon and they can't get back. They can only go out to distances of order 30 billion light years, something like that, 20 billion light years, send signals back and forth, which will take billions and billions of years, triangulate, discover the fact that things are that they're receding away from each other, but before they go too far, come back. So in principle, they can do geometric measurements, discover this curvature of space-time, discover the fact that there's a dark energy. But it would take billions of years, at least with the level of precision. I think even with better levels of precision, they would have trouble. If their astronomers are anything like our astronomers, it will take them billions of years to reconstruct the fact that they're in an inflating universe.
The yes/no version of the same question is basically, do you believe that dark energy can destroy information?
No.
Yeah, I was just thinking about gravitational attraction of galaxies. There are larger gravitational structures where galaxies may be closer together sometime in the future.
Yeah,
who's going to win there?
Yeah, I actually once asked some observational cosmologists, is it really true that all that we'll see will be us and the Andromeda? And I think it is true. I think everything else is participating in the outward flow enough that they will recede. Yeah, I think so.
If we're currently if expansion is accelerating, where is that on the curve? What's happening on that curve for expansion?
We're down there and just sitting there. Nothing's happening in this curve. Nothing.
Can you express phi as a function of time on the upper board on the right? Yeah, phi.
Can I express phi as a function of time? Why do I have to write an equation? I'm not going to write an equation. I'm going to tell you it started here, slowly drifted to the right, suddenly picked up and went down to here.
It's very nonlinear.
It's nonlinear.
It's hugely nonlinear.
Hugely nonlinear. Very agreeable. Yep, that's right. Well, it might have been linear up here, gradually linearly tracking along here. But when it got to here, yes, it became nonlinear. Okay, yeah.
You were referring before, just a minute ago about way in the future societies could actually send probes out, but with the dark energy, it shouldn't take should take at some point to where the universe is expanding faster than the speed of light.
Yeah, they can't. They must not go. They must not go past the horizon, or else they can't get back.
Right.
Yeah. Yeah.
Which gets smaller and smaller.
Yeah. So, but they can certainly go a few billion light years out and then come back, and that should be enough for them to be able to measure carefully properties. not just one of them, but a few of them sending light signals back and forth, which themselves would take billions of years to travel. They could probably do some triangulation. I haven't thought about it a lot. It's not an urgent thing on my... Yeah, yeah. It's always... No, no, the horizon will stay out there at roughly 50, 60 billion light years. I don't remember exactly what it is, but 50.
Space in that, there's just less space in that distance.
There's not space?
There's less space.
Less space? No, less stuff. There's the same space there. There's a lot of space, but not much stuff in it.
How do you define that boundary? Is it where the recession velocity of a galaxy approaches the speed of light?
Mm-hmm.
Or,
Yes.
or it's,
If you're sitting here, the potential energy is constant, and the Hubble constant is constant. Constant, Hubble constant. It means the universe is expanding this way, or it also means that distance or velocity is equal to distance times Hubble, and Hubble is constant now, so you can now solve the equation: at what distance away from us are things receding with the speed of light, and find distance divided by Hubble, c divided by Hubble is equal to distance. And what you will find will be of order 15 billion light years, right, from the known numbers. 15 billion light years, and that's where the horizon is. That's where things are receding away from us with the speed of light. Okay, yeah, all right. Boy, this lecture seems to have been very provocative.
Well, what we sort of sense about things after a lot of expansion, we'd be alone, our galaxy would be alone. What would the nature of our galaxy be? Would it be a lot tighter than it is now?
You have to ask a galactic. I don't think so. Somewhat, but not a lot. No, I think it's gonna, yeah. How many stars there will be, what the density of stars is, I don't know, but I think that will survive for 1 trillion years, and I believe. I don't know. I never was sufficiently interested to track down and ask my friends what the details are, but I think there will still be the galaxy. There will still be stars, and with any luck, there will still be planets and intelligent creatures on them.
You've spoken of inflaton as a particle. Is it correct to think of space having been filled with many inflatons in the sense that it's now filled with many other kinds of particles? And the inflatons are now gone, they've decayed into other things?
Yes. That's exactly right. To some extent, you can imagine that all this energy was stored in a kind of condensation of the inflatons, and it was released as you came down here, and the inflatons decayed. Now, again, I mean, much of what I'm telling you would have to be true in order to explain why the universe is and was the way it was during the observable period. We do not understand with any great insight why this is the picture. But we do have significant evidence now that that is what the picture was. Okay. All right, we have 15 minutes or so. The next thing on our agenda is to understand, after all this inflation, why isn't the universe completely smooth? The amount of inflation that took place in order to make it as flat as it is would have made it so smooth that there would be no explanation of the structures that are out there, the inhomogeneity that's out there today. So the next thing we want to come to is the fact that the universe is not homogeneous, and it has all kinds of structure on various scales. I thought I would tell you a little bit about that structure and just a very naive but still more or less right explanation of why the structure appears the way that it does. Now, I'm not talking and what it traces back to. When I say the structure, I don't mean galaxies now. Galaxies are small potatoes on a small scale. I mean on a much bigger scale. Not just clusters of galaxies, but whole superclusters of galaxies. And they form a structure that fills the universe that does have structure. It does have structure. It's not completely homogeneous on those scales. And that structure is quite fascinating, and I think largely understood, but it's mostly understood by simulations. The simulations start by assuming the universe was not precisely smooth, and they start with a certain pattern of non-smoothness called the fluctuation spectrum, which we're going to study a little bit, and then allow gravity and just the motion of objects and so forth to evolve and see that it creates structure. Now, on the biggest scales of super-duper clusters or galaxies, gravity is not all that important. On the scale of a galaxy, or certainly on the scale of a star or a planet, gravity is what pulls things together. On bigger scales, there's structure that's seen that is largely not, or to some extent not coming from gravity, and would be there even if there was no gravity. But what it takes is to start with some inhomogeneity, some fluctuation in space. So I thought I would talk a little bit about the theory of how that structure got formed. And the theory that I'm going to show you is extremely simple, extremely simple. I gave you 3 pictures to look at. Has everybody seen the 3 pictures? I sent them to you by email. All right. Picture number 1 is actual photograph of the sky, but deep, deep, deep astronomy. Billions of light years out, high redshifts. And what you see is a pattern of light which has some structure to it. It's not featureless. And I couldn't find as good a picture as I wanted, but what you see has a kind of filamentary structure. You can see it on the pictures, but there are better pictures. I couldn't find the right one that I was looking for. It has a kind of filamentary structure. Now, these filaments are not single galaxies. There are thousands and thousands and maybe millions of galaxies, a huge number of them, forming these filamentary structures. And the filamentary structures intersect and form a complicated web, at least photographically on the sky. And that web sort of looks. This is an exaggeration because the pictures are not that good, but it might look something like that. At the intersection of the filaments, things are particularly bright. Again, these are not single galaxies. Particularly bright at the intersections of them. There are big voids in between the filaments, the parent filaments, and that's the rough picture on scales much, much bigger than a galaxy. I've forgotten how big these cells are. I don't remember. Okay, you can look it up. Next, second picture. This is picture 1, sky, real thing. Picture 2. I will not redraw it because it looks the same. Picture 2 is simulations made by people. What do? They start with a bunch of particles. They're galaxies, but you start with a bunch of particles with some kind of spectrum of fluctuations. Fluctuations means a little bit of randomness in the velocity distribution in particular. In one region of space, they might be moving a little more this way. Another region, a little bit moving this way, traced back to some primordial variation which we'll want to understand. All right? But that's what you start with, and you let it evolve for a while. You start with uniform, a good starting point for this would be a uniform distribution of stuff, but with variations in velocity, small variations in velocity. It's the velocity variations which are the most important things. And what do you see after a time in these simulations? You see a picture which, if I drew over here, would look just like this, except sharper, clearer. Why? Because it's simulation, and you're not looking through a telescope to billions of light years, or billions of light years, a billion light years or more. You have a simulation with great detail.
What forces or what interactions are you allowing in those?
At the moment, none.
Okay.
None. None. Right. Right. I'm going to show you the theory that you would get if there were no forces. Okay. And the last picture, anybody know what the last picture is? It's a beautiful blue color.
A swimming pool?
It's the bottom of the swimming pool. Light forms patterns at the bottom of the swimming pool, and what do they look like? They look like this. Exactly like that. You would have a hard time telling the bottom of the swimming pool from simulations of galactic structure. They look very, very similar to each other. Of course, one is in 3 dimensions, and that then is a big difference. But of course, what you see is only 2-dimensional. And the swimming pool and the real universe and simulations of it have a remarkable similarity. What's the explanation of this? The explanation of this is something called caustics. Caustics were first encountered as an optical phenomenon, namely the bottom of the swimming pool phenomenon. And we can make a simple 1-dimensional version of it. If the world were 1-dimensional, caustics would just be spots. If the bottom of the swimming pool was replaced by a 1-dimensional bottom to the swimming pool, instead of seeing lines like this, you would just see spots of high intensity. Okay, let's try to explain that. Let's go through the explanation of these caustics. The caustics are the spots of high intensity, and in 2 dimensions, the bottom of the swimming pool, they're replaced by a network of not spots, but lines of high intensity. And in 3 dimensions, we'll find out what they're replaced by. But let's go through it. Let's draw a picture here. Time goes this way, or depth of the swimming pool. Depth below the surface. I'm going to plot depth vertically upward. That's because perversity. The bottom of the swimming pool is here. The top of the swimming pool is here. Okay. Here's the top of the swimming pool. But the top of the swimming pool has some structure to it from the optical point of view. There's a little bit of waviness in the top of the water. Huh? And when light rays come in, they're refracted a little bit, and so you have a sort of rough surface here, and the angle that the light goes off in different directions will vary from place to place. So here the light may go straight through, here the light may go off at an angle, here it may go off at a different angle, over here it might go up again, here it might go off over here, and so forth. Depending, I'm exaggerating it because this is an exaggeration, this being due to the random fluctuations in the starting point of the light, where the starting point of the light is the place where the light comes into the swimming pool. It hits the bottom someplace, and what do you see? You see these, in the 1-dimensional case, you see these spots of high intensity. Let's see if we can explain that. Let's call the axis down here, let's call it x, notice, we can either think of this picture as representing the light waves from the top of the pool to the bottom of the pool, or we could think of it in a totally different way. We could think of particles starting with different velocities, at t equals 0. Instead of being the top of the pool, this would be t equals 0. And instead of different angles that the light refracts through, slightly different velocities as we move along. Okay, so let's start down here. Let's say at t equals 0. Let's think of it from the point of view of particles moving. Okay, so at t equals 0, let's assume, for simplicity, that the particles are uniformly distributed with no tendency to bunch up like this at all. Uniformly distributed, but slightly different velocities as you move from place to place. All right, so let's define dn by dx is the number of particles per unit x along this axis. Dn by dx, that's the number of particles in a small dx divided by dx. This is what you would call the density of particles on this axis. And we're just going to take that to be 1. We could take it to be anything we want, but let's just say it's uniform, featureless. The magnitude of it is not important. What's important is that it's just featureless, and let's just say it's equal to 1. Now, what happens to each particle? Let's call the position of the particle after a time t, instead of calling it x, let's call it y. Up here, let's call it y. Y of t, that's the position of a particle which, let's say, started at point x. If the particles were not moving, we would just say y of t is equal to x. The position of the particle after a certain time would be the same as the position of the particle when it started, and x is just the label that labels where the particle is, where the particles were when they started. That's what we would say if the particles weren't moving. But if the particles are each moving with a velocity v, and v depends on x, the velocity of the particles depends on x, then we should add here plus a v of x times t. The particle at x had velocity v of x, and after a time t, it will have moved a distance v of xt. So here's the starting point. It started at point x, and after a time t, its new position is x plus v of x times t. Is that clear? All right. Now, let's try to compute at a later time how many particles there are per unit y. Y is the new coordinate of the particle. We're interested in the density at a later time. What we want to compute is dn by dy. We want to know the number of particles per unit y at a later time. All right, so what do? What's the trick? The trick is differentiate this equation over here, not with respect to time, but with respect to x. So we have, let's just call it y. dy by dx is equal to 1 plus the derivative of v with respect to x. Let's call that v prime. V prime of x times t. I've differentiated both sides of the equation with respect to x. What's the next step? Anybody guess? We have dn dx, and we have dy dx. What we want is dn by dy. So that's equal to dn by dx, which is 1, times dx by dy, right? But the x by dy is just 1 over dy by dx. Okay. So let's put that in. The n by dx is 1, and this factor is just 1 divided by 1 plus v prime of x times t. Where do you think these bright spots are after time t? Can you guess? They're where the denominator is equal to 0. This is the density after time t. And where is it going to be big? Of course, in the geometric optics approximation, we're going to get something infinite. In the wave theory, it's not really infinite. We're going to get bright spots, especially bright spots, at the places where 1 plus v prime of x times t is equal to 0. Okay, let's think about that. Let's see if we can figure out what that looks like. Yeah, let's plot v prime of x. Here's v prime of x, and it varies. Remember, it varies. What does it average around? And you got a good idea for what its average might be? 0. Let's assume it's 0. So v prime of x, v prime, not v of x, but v prime of x is something that might sort of fluctuate as you go from one place to another. In some places, the particles are moving to the right. That's when in some places v prime is positive, in some places v prime is negative. And when do we get in trouble? In other words, when does this thing become infinite? It becomes infinite when v prime of x times t, or minus that, is equal to 1. Okay, let me, instead of plotting v prime, I will plot minus v prime, just because of this sign there. I told you this was v prime. Actually, I made a mistake. It's minus v prime. Okay, this is minus v prime, and here's 1 up here. And after a small amount of time, v prime times t is small. V prime times t after a tiny amount of time is small. Let's just shrink this by a small number t. And there's no place where it's going to pass through 1. Okay? But now what happens as t starts to increase? V prime of x times t increases. It just gets multiplied. So after, let's say, 10 seconds, it's now somewhat bigger. It's like this. Everything is just 10 times bigger than it was at 1 second. Still, no crossover points. This is not intended to be periodic particularly. It's intended to be more random than that. But accidentally I drew it as random. Time keeps going on. V prime times t keeps getting bigger. Eventually, one of these points, let's say this one, will get up over to here. And what happens at that point? V prime times t has become equal to 1. The denominator has become 0. When the denominator becomes 0, that's where you get a lot of intensity. That's where the intensity, the number of intensity, if it was light rays, it would be intensity. If it's particles, you get a huge enhancement of the particle density at that point. So over here, an extra strong density of particles or an extra strong density of light hitting the bottom of the pool. And the rest of them are still down here somewhere. You go a little further, this point splits into 2. This one comes up there and eventually goes through the top of the ceiling here and creates 2 more spots. These are caustics. These are what caustics are. They're places, you know what caustic means, the literal meaning of the word caustic. It means sharp. It's where these sharp features, these points along the bottom of the one-dimensional swimming pool get these very, very sharp light spots. Okay. Now, if you were to do exactly the same thing in 2 dimensions, and we could work it out, but we don't have time tonight. If you did it in 2 dimensions, where you start with a 2-dimensional world and particles moving upward, 2-dimensional world being either a 2-dimensional world or the top of the swimming pool, and you evolve either in height or in time, what you see is basically this. There are, I'll call them hot spots, I don't know, but they're not spots, they're line-like. And they intersect. And you can see that at the bottom of the swimming pool. And in fact, in the bottom of the swimming pool, you'll find extra brightness at the place where they intersect. So you get a network of lines and spots with the highest intensity being at the spots, high intensity along the lines, and big voids. Now in this case in the swimming pool, it's not voids of water, it's voids of light, missing less light. In 3 dimensions, if you play exactly the same game, now we're saying we're starting with a 3-dimensional world with a uniform distribution of particles but velocity dispersion of the same kind. What you'll get is surfaces. Surfaces intersecting other surfaces in a complicated form. Surfaces, the caustics will be surfaces. The surfaces from time to time and place to place will intersect along lines, and the lines will intersect along points. That's what you're seeing when you look at these simulations. You can't see the surfaces because the surfaces are just in front of you, but you do see the lines and you do see the hot spots where the lines intersect. The caustics. So this is what you would expect. In a world without gravity, no gravity's been invoked. All we've invoked was a distribution, a somewhat random distribution of very small velocities at the starting point. Now, it wouldn't hurt to also have some variation in density along here. It wouldn't make much difference. Basically the same thing. And that's, if you like, a very simple but not wholly inaccurate theory of very large scale structure, caustics. On smaller scales, of course, gravity plays a big role and causes things to condense into galaxies and so forth. But the point is, the reason I emphasize this is because we have to have a theory of this variation in the initial velocity distribution. And where did it come from? We've said that we've stretched the universe out to the point where it's incredibly flat and uniform. Where did this come from? Where did the starting distribution of random variations, not random, but variations in velocity come from? That in itself is an inhomogeneity. So the next thing we're going to study a little bit is the quantum origin of the inhomogeneities in the universe and how it led to the starting point for this. Good, okay.
For more, please visit us at stanford.edu.